I'm grateful to organizers for the invitation to take part in this conference. And I would like to talk about potential theory of some Markov generators. And this Markov generator has the following form. Look at this. Maybe I will put this Markov generators here. So L, f of x, this is integral over x, f of x minus f of y, dn of y. So these are Markov generators of interest, where x is a good, nice, x is nice, ultrametric space. Ultrametric space. Okay. The motivation to consider potential theory of such operators, well, actually I know two motivations. The first motivation, the first motivation is study of random walk on discrete groups having infinitely many generators. Random walks on infinitely generated groups. So, for instance, Markov generator of simple random walk on any such a group has this form. Has this form. And second motivation, some applications in mathematical physics which are due to Vladimir Volovich and others. What I want to do, I want to estimate hidden kernel related to these operators. Hidden kernel means that I want to study transition, the corresponding Markov semigroup this is Markov semigroup because of special structure of this operator. This semigroup generates Markov process. And I want to prove and to estimate its heat kernel. That means I want to say something about its transition density. So I want to say something about this function. What I'm going to do, so first of all, I'm going to study special class of such operators. I want to assume something about this kernel. This kernel has special names. This is so-called jump kernel. And people which are working in theory of Markov process, they understand what it means. So this is purely jump Markov process, and this function describes intensivity of small jumps. Okay? So I want to assume, I want to study special class of operators, and then I want to prove some kind of stability result. So if I have two operators, and if the jump kernels are comparable, then transition functions are comparable. This is the kind of well-known Aronson result about diffusion in Euclidean spaces. So this is well-known result that if you have, if diffusion matrix is comparable to diffusion matrix of Wiener process, then heat kernels are comparable. Heat kernel exists, and these heat kernels comparable. Gaussian, the so-called Gaussian bounds. But this is non-local operator, so there are difficulties in this direction, and that's what I'm going to discuss here. First, I want to describe a class of jump kernels where I can indeed compute, prove that transition density exists and compute this transition density. So, let's see. These are so-called isotropic generators. So, roughly speaking, these isotropic generators have this form. Okay? They have this form. And jump kernel is indeed depends on the distance between x and y. Okay? In special way. Then, if I have this structure of jump kernel, then one can prove that transition density exists. This is deeply non-trivial fact in general. Okay? And that this transition density even can be represented in the form. So equation number 1.3. Okay? But having this integral form, I can estimate the transition density P. Let's see. So, once again, the aim of this lecture is to present recent result of two-sided bounds of heat kernels which have comparable to this class jump kernels. Okay? So, that's how I want to introduce isotropic operators. I call this Laplacian. Why Laplacian? Because this operator satisfies maximum principle, so this is general definition in abstract potential theory. So this operator acts on locally compact and separable parametric space, and this space has special property. So this is like Cantor set. Okay, so this is example. This is example of ultrametric space or Cantor set. So you take partition of the Euclidean space made of periodic intervals, and you define distance in a special way. It is written here. So as you see, you are working with Euclidean space, but you change topology. And thanks to this change, topology becomes very different from Euclidean one. So now this space is going to be not locally connected space. But you did not destroy Borel sigma algebra. This is a well-known example. Okay? So I'm going to define the Laplacian operator. To each ball, associate some number. This is function C. This is so function C, function of coefficient, and this function has to satisfy some certain properties. Okay? These two properties are written here, equation 4 and 5. Very natural. I will give you many examples. And then we consider the set of test functions. Okay, the set of test functions, these are functions which are locally constant and have compact support. I need radon measure with full support, and then I define hierarchical Laplacian as convex linear combination of elementary Laplacians. You see in brackets, this is elementary Laplacian or Poisson generator. Okay, so this is operator. Then you need some work to prove that this operator is well defined, symmetric in L2, and in fact it admits a complete system of eigenfunctions, which people in this area call Haar functions. Okay? So you see, this operator has a complete system of eigenfunctions. That's why it is essentially self-adjoint operator. Now to say something about its transition function, its resolvent, I need to change ultrametric. This is known in general theory. To each operator, you can associate its intrinsic metric, the so-called Carnot-Caratadori metric. Okay? So in this case, this intrinsic metric looks like this. Lambda x minimum y, this is minimal ball which contains x and y. And lambda is the corresponding eigenvalue. Okay? As you see, this is new ultrametric, and it has the same set of bonds, but change distance. Okay, this intrinsic ultrametric eigenvalue look like 1 over diameter. Now we define spectral function using spectrum of this operator, and we define volume function as usual. And then some work, and you're going to prove that transition function is absolutely continuous with respect to reference measure M, and it admits density, and this density has the following form. Okay, equation 2.11. And then you will also estimate resolvent, and even so, you answer when this resolvent exists at lambda equals 0, and you are going to write green function in terms of volume function. This is very common in potential theory. Okay, volume function play a very important role. Now, in fact, using these formulas, 11 and 13, you would like to obtain nice bounds on the heat kernel. So here we are, fact number 1. If volume function is doubling, then you obtain stable like bounds of the heat kernel in terms of volume function. Okay, so to prove this, you need some work, but it can be done. And also you can estimate green function. Okay, and here is example how to create such a nice operators. You define coefficient function, and then making some assumption about function phi, you are going to prove these bounds. Of course, you apply general bounds. You see, these are stable like bounds. Now, hierarchical Laplacian at the very beginning does not have this form, right? It's a convex linear combination of Poisson operators, Poisson-like operators. I call this elementary Laplacian. But in fact, you need some work. You need some work. And you're going to prove that any hierarchical Laplacian has this form. with jump kernel which depends only on distance between x and y. And vice versa. And vice versa. Okay? So if you have isotropic Laplacian, then you can prove that with isotropic jump kernel, and this jump kernel must be monotone, then you will prove that this is hierarchical Laplacian. Now example. So let us consider the field of periodic numbers with its natural distance. And let us, this is a abelian group, so you can define multipliers of this form. There is Fourier transform, so this is class of multipliers. And you're going to prove that each multiplier of this form, if symbol is monotone, then it is hierarchical Laplacian. And you obtain its heat kernel bounds and jump kernel bounds. It depends on function phi, of course. So there are two well-known multipliers. These are so-called Tablison-Vladimir multipliers, which were introduced by Tablison and Vladimir. These are two books, Fourier analysis on local fields, and Vladimirov in Успехах, Russian mathematical services. So you see, it looks like fractional power of Laplacian. And then heat kernel and jump kernel have bounds like in Euclidean space, like fractional powers of Laplace operator. Okay? And one more example. Vladimirov multiplier. You see, this is like some derivatives over variables, x1, x2, and x3. D alpha, this is like fractional derivative of order alpha. So Vladimirov introduces his multiplier. So as you see, symbol of this operator looks like actually comparable to periodic norm of Xi. So this is operator of this kind, but jump kernel is not absolutely continuous with respect to reference matter. It is actually singular. It is not hierarchical Laplacian. But one can prove that the corresponding Markov semigroup admits a continuous heat kernel, and green function is comparable to alpha stable generator. But heat kernels do not comparable at all. Okay, this is Vladimirov multiplier, related very much to periodic aspects of quantum mechanics. Okay, there is paper, recent paper in Russian math services. Now, isotropic light generator. So right now I want to introduce operator of this kind. Okay, but in order to prove something about this operator, I have to assume something about jump kernel. So, how can I introduce this operator? I want to prove that this operator actually exists, symmetrics of a joint or whatever. Of course, I use quadratic form. So, having jump kernel, I create Dirichlet form. This is formula 25. So I have to say something about this Dirichlet form. For instance, I would like to prove that this form is closable, and then I will take its minimal closed extension. And I want to say something about this form. Okay? Then I am going to apply general theory of Dirichlet forms and to prove that this Dirichlet form corresponds to some Markov semigroup, and it can be represented in the form equation 26. Okay? I will give you the sufficient condition. So this is like in general theory of Dirichlet forms. You define some Dirichlet form, you prove that this is regular Dirichlet form, then there exists L2 Markov semigroup, but then you are going to spend a lot of effort to prove that in fact this L2 semigroup can be understood pointwise and correspond to some Markov process. This is the main difficulty in this theory. So that's what we are going to do. Well, that's what we are going to do. Actually, we are going to prove Aronson type theorem for non-local operators. This is paper of Chen, Kumagai, and Wang, and also recent paper of mine and Alexander Grigoryan and Professor Hu. So this is theorem, the main. Assumption assumes that this jump kernel is comparable to some isotropic jump kernel as above. Okay? This is monotone isotropic jump kernel. And let us consider volume function associated to this isotropic jump kernel. And let us assume that this volume function is indeed doubling. Then you are going to prove Aronson type theorem that L2 Markov semigroup is in fact can be understood pointwise, and that it admits a Hölder continuous heat kernel, which is comparable to isotropic heat kernel. Okay. This is completely non-local analogy of Aronson's theorem. In Aronson's theorem, you compare diffusion matrices, and here you compare heat kernel. And the effect is the same. So, some example. You consider hierarchical Laplacian. Hierarchical means that jump kernel depends on distance and is a monotone function. Monotone symbol. And you consider bounded function measurable, and you consider this operator. You see, you change coefficient. You change coefficient. People which are working in Markov processes, they understand what that means. You change time. Okay? Okay, let's see what we can prove for this operator. So, if you change measure, then this operator can be written in this form with symmetric function j. And function j looks like AJA, so it is comparable to j function. So we can apply our general result about stability. You can estimate heat kernel with respect to measure m tilde, and that means that you can prove existence of heat kernel with respect to m, and actually give bounds for this form, for this heat kernel, non-symmetric heat kernel. So this is a kind of uniformly elliptic operator. You see, you change coefficient. Okay, so, okay, so let me mention.
Но если вам нужно чуть больше, то можно дать, так сказать.
Да.
Значит, очень
Ну, я постараюсь.
Да.
Не напрягу. Let me mention one more problem. So, let us consider field of p-adic numbers. So this is locally compact abelian group, totally disconnected, a Cantor-like group. So there is class of infinity divisible distributions, and there is Levy-Hinchon theory. And it is very important, very interesting to prove that given infinity divisible measure has density, to estimate this density, think about stable distributions in Euclidean space and Polya result. This was first result who gave you bounds of alpha stable densities. So there are alpha stable densities here as well. This is abelian group. That's what I want to discuss. And you see, thanks to Levy-Hinchon formula, any infinity divisible symmetric distribution can be written in the form. Why? Why? Because this is totally disconnected group and there are no Gaussian distributions. Okay? Totally disconnected group. So Gaussian quadratic form is absent in the Levy-Hinchon formula. So that's how it look like. This is Levy-Hinchon formula in terms of Levy generators. Okay, a kind. So I refer my audience to the book of Berg and Forst for Levy-Hinchon theory. So we would like to analyze some analytic properties of infinity divisible distributions. Of course, we want to start with infinity divisible distributions which are isotropic, like symmetric stable, like, okay, symmetric stable. You see, these are exactly our isotropic distributions. So we know everything about this, we know many things about this distribution. So the generator of each such distribution looks like function of the fractional derivative d. Okay, so for this echelon class of distributions, we know that that density exists with respect to Haar measure, and it can be estimated in this way, and jump kernel as well can be estimated. Now, jump kernel, this is Levy density, okay? Jump kernel corresponds to Levy density in this theory. Okay, so that's what we can extract from our general theory. And now we can apply our comparison technique. So we consider infinity divisible measure and the corresponding quickly continuous convolution semigroup. And there is Levy measure, and we assume that Levy measure is absolutely continuous with respect to Haar measure and is comparable to isotropic symmetric Levy density. Then mu t is absolutely continuous with respect to Haar measure, has density, and this density is comparable to isotropic density. Okay? But there are many examples where there are many examples where jump kernel might take 0 values on some non-trivial sets. For instance, take simple random walk, so it jumps in direction of generators. It takes many 0 values. So our theory in this case does not work. Because our etalon Levy density is everywhere positive. So what to do in this case? So, well, some partial results are already obtained in this direction, and I do not have time to talk about this. So the point is that you are going to compare Dirichlet forms, you are not going to compare Levy densities. Levy measure is singular with respect to Haar measure. So at least you can compare Dirichlet forms. Okay? Then, so this is a recent paper, and I hope it will be published very soon. Thank you very much for your attention.
The question is, comments, please.
Can we compare this formula with Balakrishnan formula?
Which formula?
Balakrishnan formula,
Which formula we want to compare with Balakrishnan?
as shown, which shown on the desk. If we
On the desk?
yes,
This,
yes.
can we compare this generator of such a form with
With Balakrishnan formula for fractional powers of if we suppose a particular case for jump function, we can reduce the formula. It seems to me possible, but I'm not
Balakrishnan
sure.
formula, there is integration over resultant.
Yes.
So actually, having something, you want to compare resolvent with some other resolvent, well, it is possible, as I show you. Yes, if you have comparison of jump kernels, then in some cases you have comparison of resolvents, green functions. And then you can, of course, apply Balakrishnan formula in order to work with,
Fine.
well, in some Banach spaces, not in M2. Right? That's what you asked.
More questions or comments, please? In such a case, we have a small but sweet present.
Thank you very much. Thank you again.